everyone. Welcome to this week's Crunch seminar. And today, as usual, we have two speakers. So our first speaker is Dr. Youngsoo Choi. So Dr. Youngsoo Choi is a computational scientist in Center for Applied Scientific Computing Division at the LLNL, the Lawrence Livermore National Laboratory. His research focus lies on developing efficient data-driven methods of accelerating various physical simulations to be used in time-sensitive decision-making applications. And currently, he is leading a data-driven surrogate model development team at LLNL. So today, he's going to give a talk with the title Data-Driven Methods of Accelerating Physical Simulations and Their Applications. So let's welcome Dr. Youngsoo Choi.
Thank you. Thank you so much for the great introduction and for the invitation to very famous, the place. And it is an honor to present our work here at Crunch Seminar Series at Brown University, which is the birthplace of the PINS. Today, PINS is the rising star in machine learning based the physical simulation, right? I'm going to talk about data-driven methods of accelerating physical simulations, the surrogate models. I assume that most of you are familiar with surrogate models already, so I will rather focus on kind of giving you what we have developed at Lawrence Livermore National Lab and where we are going with these surrogate models techniques. Okay, some brief outlines of the talk today. In the beginning, I will introduce two types of surrogate models, non-intrusive and intrusive surrogate models, and then I will start to give examples of non-intrusive models first, and then switch gear to intrusive surrogate models, so-called reduced order model. Okay, as you all know, we live in an exciting time. The machine learning and artificial intelligence surprising us with its capability and improving the convenience of our daily lives here and there, right? For example, I believe you all remember the machine learning based Go player, AlphaGo, defeated a top professional Go player, Lee Sedol, from South Korea. That was scary, personally. Artificial intelligence did not stop its advance there. Now, the machine learning is enabling self-driving car and advanced speech recognition. But for now, I don't think you want to sleep in a self-driving car, but in the future, the technology will continue to advance, and for sure, you will be able to sleep in a self-driving car with some guaranteed safety. By the way, all these applications were, where the first principles hardly exist. So people, it's obvious the application, next application was to applying the machine learning and artificial intelligence in the physical simulation sections where the first principles, exist. It's the people are continually the developing the new algorithms, and someday I think this effort will pay off. I think the PINS is already one result of those efforts, and I anticipate that this effort will continue to further advance the machine learning based scientific applications. And today, I'm going to focusing on the surrogate modeling, whose goal is very specific. And just to set the stage, why surrogate model, right? Just to give you a motivations for the surrogate model, you are looking at a beautiful simulation modeled by smooth particle hydrodynamics for shape charge penetration, which is simulated at Lawrence Livermore. The simulation is well matched with the experiments, but very expensive. One-fold simulation takes 7.4 days using high-performance computing facilities here at Lawrence Livermore National Lab. And this is unfortunate in multi-query applications, such as design optimization, optimal control, inverse problems, where you need to query and run these fold simulations many times. Therefore, many have tried to build an efficient surrogate models that accelerates these simulations without losing much accuracy, right? And another motivation can be given due to the climate change. Temperature is increasing, and therefore for example, ice in Greenland is melting, and the sea level is rising. So in order to better predict, and possibly prevent the disturbing the rise of the sea level, we need an accurate ice sheet model. For example, this ice sheet simulation for Greenland takes 16,000 cores and 1 billion degrees of freedom and takes 400 seconds for one time step. And typically you will want to run the model for decades and centuries. And there is a pretty restrictive CFL condition. So imagine how expensive it would be for one fold simulation, right? So if we talk, and even more, like if you talk about the inverse problem where we need to find out, for example, basal friction and ice thickness, many fold simulation needs to be run. Furthermore, if we talk about some Bayesian optimization setting where uncertainty needs to be incorporated, this is simply intractable. So we need surrogate models to accelerate these simulations. Okay, these were the motivation for the surrogate model. A surrogate model can be built by first considering a parameter space. The parameter space can be initial condition, boundary condition, or material properties of climate modeling. Then you collect data by solving full order model for several sample points, right? Then you apply machine learning techniques to build surrogate model. Various machine learning techniques are available as listed here: principal component analysis, Tucker decomposition, canonical polyadic decomposition, autoencoder, generative adversarial network, etc. So as you can see, various surrogate modeling types are possible, but depending on how much you incorporate physics law in your surrogate model, it can be intrusive or non-intrusive. I will go over some advantages and disadvantages of intrusive and non-intrusive methods later. But for now, going back to the procedure of generating the reduced total model or the surrogate model in bigger terms, you can accelerate the simulations using the surrogate model in various query points here and there, and many more which you haven't seen in your training phase. And it's obvious that it can be useful in multi-query applications, right? These surrogate models can be categorized by its level of intrusiveness. For example, black box approach, denoted as BB, is the least intrusive method, requiring only data. Then we can think of more intrusive methods. First, linear subspace reduced total model, so-called LS-ROM, where the state fields are represented by a compact linear subspace. And even more intrusive method, that is nonlinear manifold reduced total model, so-called NM-ROM, where the state fields are represented by a compact nonlinear manifold. But roughly speaking, more intrusiveness means more accuracy. So reduced total models are more accurate than the black box approach if the same amount of data are used. On the other hand, more intrusiveness means less speed up. So the black box method is faster than reduced total model in general. Okay, now let me give two different but somewhat similar black box approach, linear multi-step neural network and deep fluid. Both of them directly approximates the state outputs, by the way. And they follow the same, more or less the same framework, where you start with the simulation data here, right? And then compress the data into the low dimensional latent space, and then reconstruct the full data by decompressing them. For the compression, there are many dimensionality reduction techniques you can apply. In general, they can be divided into two categories in terms of the reduction type, the linear subspace representation and the nonlinear manifold representation. And the first example I would like to show, which is the linear multi-step neural network, utilize the linear compression technique, which is the POD, propo-orthogonal decomposition, to demonstrate that, let's say we have a airfoil flow data, as you can see here, and we use singular value decomposition to obtain a reduced basis for your state fields. Then project the original airfoil flow W onto the subspace spanned by the reduced basis and obtain the reduced data A. Then the linear multi-step neural network is trained using the reduced data A. So you work on the reduced space to train this neural network in time, to propagate in time. And then once you get the reduced space solutions in time, you reconstruct the full states by applying the reduced basis phi to the reduced solutions. As you can see, we only use the data throughout the whole process. So it is black box approach, but directly approximates the whole state fields. Here is some numerical results, and comparing the full order model solutions and the black box surrogate models using the linear multi-step neural network. And as you can see in eyeball norm, they are very similar, but at the same time, the surrogate model was able to generate the solutions within 2.55 seconds, and the full order model took 314 seconds, which gives us the speed up of 100. And quantitatively, the relative error, the relative error was less than 1% everywhere. So it's pretty good. And the next, the black box approach I would like to introduce is the deep fluid, where the nonlinear manifold learning algorithm, that is autoencoder, is used for compression and decompression of the solution data W instead of the linear subspace the reduction method, which is the POD. In autoencoder, the encoder compresses the input data to latent space, and decoder decompresses the latent space data to obtain an approximate solution. The overall autoencoder parameters are trained by minimizing the difference between the input and the outputs. And then the autoencoder is trained for, once the autoencoder is trained for the predictions, we apply again the latent space integrator to propagate in time in the latent space. Since the size of the latent space is small, this time integrator will be fast. After you get the latent space solutions, we restore or reconstruct the full state by applying the decoder, right? And we have applied this black box approach to 2D Burgers equations, where the simulation is very advection dominated, and the shock front is formed from the corner and propagate to the rest of the computational domain. As you can see from the movie, the full order model and deep fluid solutions looks very similar in eyeball norm, while the deep fluid gives a speed up of greater than 100, which is very good. However, the deep fluid gives a maximum relative error of around 38.6%, which might be good for graphics applications. However, it might not be good enough for some scientific applications. So I will show how to reduce this error tremendously by applying a reduced order model technique.
Youngsoo, can I ask a question? It's not clear is this just a reconstruction of the field, or is it different Reynolds number or different in this example? Are you simply reconstructing?
Oh, no, this one is not reconstructing. Okay, so the Reynolds number was fixed to 10,000, but we changed the initial condition. We used the initial condition as a parameter, and then this comparison was, the testing cases, not the training cases.
Oh, so it was a different initial condition. Different initial condition. Okay.
Exactly. Yeah. So it was the predictive case, not the reproductive case. Okay, so
can I ask on that, because that's important, right? What kind of initial conditions did you have here to train it? Is it a certain space or arbitrary? Is it like some perturbation of the initial condition? How do you define the
Yes.
space?
Right, exactly. So we use the sinusoidal initial conditions, and then for this one we change the amplitude, and I'm not sure we are changing the location, but yeah, in the past we have changed both of them, the location of the the pulse, the initial pulse, and then the amplitude of the amplitude of the initial condition, the shape of the initial condition. That was so basically we use the geometric parameter.
Okay, thank you.
Okay, let's switch a gear and talk about linear subspace reduced to the model. Next 2 to 3 slides, I will go over some technical background on reduced to the model, and then introduce some challenges we encounter with the linear subspace reduced to the model, and then introduce some variants to overcome those issues. Okay, here I'm going to introduce the projection-based reduced to the model, very traditional types of the reduced to the model. To do that, we will start with this governing equation represented by the ordinary differential equations. Here, W is a state variable, F is a nonlinear function, and T is the time variable, and mu is a parameter. We first approximate the solution as a linear combination of reduced basis phi, whose dimension is a lot smaller than the full order model dimension, big and so vast. Then you plug this solution representation into the governing equations. Then you will end up with an overdetermined system where you have more equations than unknown, right? So to close the system, you apply some kind of projection here. Here I have applied the Galerkin projection that gives a reduced system of ordinary differential equations. Then you can apply your favorite time integrator. Here I have applied the backwards Euler time integration just for the demonstration purpose. This gives us the fully discretized reduced system of equations you have to solve in every time step, right? Now you see there is a nonlinear function f here. Every time the argument of the nonlinear function changes throughout the Newton types of iterations, you have to update the nonlinear function and multiply it by the phi transpose. Unfortunately, that scales with the full order model size. It turns out that if you solve the reduced order model in this way, it is actually slower than the corresponding full order model, right? So what is the point of introducing these projections and reduce the number of equations and unknowns if the process is slower than the full order model and it only gives an approximate solution at the end anyway, right? So people have developed a technique called the hyperreduction to reduce the complexity of the nonlinear function. The most famous hyperreduction technique is DEIM, which stands for discrete empirical interpolation method. The DEIM introduces the nonlinear basis phi of f and then express the nonlinear term as a linear combination of nonlinear basis vectors. Then it introduces a sampling matrix Z, which selects an important subset of the nonlinear terms. So after the action of Z on nonlinear term F, only the subset of F will be evaluated. Now the sampling, the indices of the matrix Z can be obtained through various algorithms. DEIM and QDEIM are the popular ones. And once you obtain that, the generalized coordinates for nonlinear term f of hat can be obtained by solving the interpolation problem. Then you plug this expression into the reduced system of equations wherever the nonlinear term shows up. Then you will end up with this somewhat crazy looking equations, but if you look at closely, a lot of terms can be pre-computed. And this nonlinear term can be efficiently computed because of the sampling matrix Z in front of the nonlinear term F. Okay, this is how you achieve the efficiency through the reduced order model and the hyperreduction. There are many variants of the DEIM. For example, GNET and ST-GNET are others. But the main machinery of the hyperreduction follows this paradigm that I have just introduced here. Okay, this type of reduced Dodo models have been successfully applied to many different physical simulations. In spite of these successful applications, though, it has some major drawbacks. Let's look at the simple pure advection simulation where the rectangular pulse simply moving from left to right, right? Unfortunately, the current linear subspace reduced order model cannot represent the solution span of this simple simulation. It is not hard to see why, though. The individual snapshot data from the pure advection simulation is linearly independent to each other, as you can see. So there is no way for the linear subspace basis to be able to represent this solution span compactly. Simply, you must include all the snapshots in the reduced spaces to accurately represent the solution span, which is unfortunate and which is not reduced to the model anymore. These numerical results demonstrate how LS-ROM, the linear subspace ROM, suffers from the advection-dominated problem. This is the same, the 2D burgers problem you have seen before. We have used the latent space dimension of 5, which is pretty small, which might be challenging for LS-ROM to produce the good accuracy because of the reason I just described in previous slides, right? As we expect, the movie shows that the LS-ROM exhibits some fictitious oscillation in front of the shock wave, resulting in a relative error around 34%, which is somewhat better than the black box approach I have shown you before. However, it might not be good enough for the many scientific applications. So now, how can we improve this? If you think about it, it is the linear subspace that is unable to represent the advection-dominated solution with a compact basis. So it is natural that we transition from linear subspace to nonlinear manifold when you represent the solution. But how would you build a nonlinear manifold solution representation? Here comes our friend machine learning, more specifically neural network. And that is, let me skip this one. That is how we came up with this nonlinear manifold reduced model. Let's go into the content directly. To explain the nonlinear manifold reduced model, here is the governing equations you have seen before, the ordinary differential equations. Again, W is your solution variable. Now we approximate the solution with nonlinear manifold, some nonlinear function, which maps a small latent space dimension to full order model dimension, this G function, right? But somehow you have to come up with this nonlinear function G. How do we do that? We obtain that by training a autoencoder using the solution data, as you have seen from the deep fluid approach, right? Now, after you train the autoencoder this time, you take this decoder, and if you look at the decoder, it is mapping the small latent space to the big space. So that is a perfect candidate for this nonlinear function G. So this decoder we use as our the G function, and then we plug the nonlinear manifold solution representation into the governing equations and obtain this overdetermined system again. Now, since you have an overdetermined system, you have to close the system. And there are roughly 2 ways of doing that. The first one is the Galerkin, the projections, where you first obtain, apply the projection first, and then obtain the reduced ODE, and then apply the time integrator to fully discretize the reduced nonlinear system of equations. On the other hand, the least squares pattern of Galerkin swap the order. You first discretize the nonlinear system in order to get the nonlinear, the fully nonlinear system of equations. But there are more equations than unknown. So in order to close the systems, we apply the least squares problems, and by minimizing the residual of that the nonlinear the discretization, this fully discretized problem, and then obtain the latent space. Here, many crazy looking terms exist and it appears, but those can be pre-computed as usual. And thanks to the sampling matrix Z in front of the nonlinear, the residual terms of tilde, this can be efficiently computed. However, because we have introduced the nonlinear function, the G, we have to pay special attention to the structure of the neural net, because that matters for the efficiency of the nonlinear manifold reduced model. So let's first look at the neural network with two hidden layers, just for the demonstration purpose. And then let's assume that this orange disk, 3 orange disk, is chosen by the sampling matrix Z, and those outputs are the only outputs you have to compute for the hyperreduction. But if you have more and more hidden layers, and more connections are involved in those hidden layers, you can easily imagine that there are many more hidden nodes you have to go through in order to compute those chosen outputs. So even though in outputs we have chosen, okay, in hyperreduction we only need these 3 outputs to compute to efficiently reserve some accuracy of the nonlinear manifold reduced model. But because of this hidden structure of your neural net, the overall computation becomes actually very computationally demanding. On the other hand, if you choose the shallow neural network, and if you sparsify the connections, then the hidden nodes involved to compute those selected outputs are small. The number of them is small. So therefore, the Jacobian computation of the neural net will be can be efficiently computed, and the overall the nonlinear manifold reduced model can be used to accelerate the physical simulation. So this is exactly how we achieve the efficiency in nonlinear manifold reduced model. Okay, so here we compare the performance of all the surrogate models that I have introduced in these presentations, including the nonlinear manifold reduced model and NNROM. As you can see from the movie, NNROM and Flodo model are almost identical in eyeball norm. Quantitatively, the nonlinear manifold reduced model achieves less than 1% the maximum relative error compared to the Flodo model solution. Furthermore, the considerable speed up, like around 11, although it's smaller than the 26 or 100, but it's still considerable, knowing that the reduced model has been applied to this small problem, 2D Burger's equations, and our back of the envelope calculation shows that this NNROM will achieve a better speed up as we apply this technique to larger scale problem. Okay, so if you, however, somehow think that NNROM is too complicated because you have to introduce some more nonlinearity in your governing equations. I mean, on top of the nonlinearity in your governing equations, you are adding more nonlinearity, right? So, and also it is, the approach is intrusive, unlike other, black box approach. So, that's why people are hesitant to apply this type of, the nonlinear manifold reduced model to their applications. So whatever the reason is, if you think that NNROM is too complicated and you'd like to stay in linear subspace reduced model regime and still tackle the challenge caused by the advection dominated problem, we do have options here. And the first option is to apply a time windowing reduced model. And the idea of behind the time windowing is very simple. And because you need to include all the data in linear subspace reduced to the model, if the simulation is advection dominated, you just divide the time domain into several subdomains and build the local reduced to model for each time window. Since the each time window, you only have to represent the amount of the small amount of the solution space. Therefore, the local reduced model size will be small and will accurately represent the advection dominated solution. And once all the local reduced models are constructed in the training phase, in online phase, depending on where the simulation is, you invoke the appropriate local reduced models and use it to propagate in time. As I said, the idea is very simple, right? And we have applied this time windowing reduced model to Lagrangian hydrodynamics. Since it is Lagrangian, your mesh is moving, so we have to introduce the position fields and also corresponding velocity fields, and there is an energy field and three different fields you have to incorporate, and we introduce the reduced basis for each field separately, and then also apply the time windowing approach for each time domain. Okay, here the full order model and its data are generated by the open source code Lagos, and for these problems we use the total degrees of freedom was 14,000 and the energy degrees of freedom was around 4,000. And it takes, the full order model takes around 400 seconds for one-fold simulations. As you can see from the movie, both the full order model and the reduced order model solutions are more or less the same. For the reduced order model, if the no time windowing approach is used, it still captures pretty good accuracy, but it is slower than the full order model as expected. However, if you apply the time windowing approach, then we can finally achieve a speed up of 4.6 with reasonable accuracy. And the great thing is about the reduced model, its accuracy can be tunable. So if you want more accurate solutions, we can add more bases or the more sampling points in hyper reductions, and then increase the accuracy, and then but you have to pay some price on the speed up. So speed up was decreased from 4.6 to 3.8. Okay, this type of time windowing reduced model has been applied to other hydrodynamics problems. For example, triple point problem and the Taylor-Green the problem, and then the Rayleigh-Taylor instability problems. For all cases, we were able to achieve the reasonable speed up and accuracy using the time windowing reduced model. Okay, and of course, it's related to George's the previous questions. The reduced model is not useful if we can only reproduce the full order model solutions. So in order to demonstrate the predictability of our reduced order model, here we have varied the initial blast energy from like some small number to 0.5, and the reduced model was generated at 0.25, and we plot the graph of the relative error, and as we expected and anticipated, our reduced order model is most accurate where the ROM was trained, right? But if you go farther from that point, the accuracy is degenerated. That means if you are dealing with a local reduced order model, each local reduced model has some sort of a trust region. So depending on the applications, if your application is okay with a less than 1% relative error around this line, then the trust region for this local reduced model will be around 0.1 to 0.4. So if you want to build a reduced model for more broader range of the parameter space, for example, beyond 0.4, then you can build another local reduced model around 0.6 to cover your parameter space, so that overall the accuracy is less than 1%, right? Okay, the technical paper of the reduced model, the Lagrangian for this Lagrangian hydrodynamics can be found in archive preprint, and where you will find many more interesting numerical examples than I have presented here. And also there we also introduced the hyperreduction technique called the SNS, and there you will also find the error bounds for the reduced model we have developed here with adaptive time stepping. That was kind of tricky to do those analysis, but you can find the details about that, and please check out this preprint. And also the code implementation is available in GitHub, so you can check that out, those the code from the repo. Okay, another way of overcoming the issue caused by the advection dominated problem is to use space-time reduced model. The space-time reduced model tries to reduce not only the spatial degrees of freedom. Remember, so far we have only tried to reduce the complexity in the spatial domain. However, for the dynamic problem, there are temporal degrees of freedom also, right? So if you can reduce both space and time domain altogether, then you will obtain optimal reduction. And we can do that by introducing a space and time reduced spaces. They are combined. They can be combined with a canonical product to represent the whole space-time solution space. And then the coefficient in front of, W hat here, coefficient in front of this space-time reduced basis will be computed in the reduced order on the space-time reduced order online phase. And those coefficients can be computed by taking the norm of the space-time residual vector and then minimize it in least square sense. And that's how we did that. And of course, if it is the nonlinear problem, we have to introduce the sampling matrix for the sampling matrix G hat to efficiently handle the nonlinear terms. Or more or less, that's how we construct the space-time reduced order model. Okay. All right, we have applied this space-time reduced model to pretty large-scale problem. This is a Boltzmann the transport problem. It is linear, but the number of degrees of freedom is pretty high. For these specific problems, we have a 600 million degrees of freedom and 10 billion the total degrees of freedom if you include the temporal degrees of freedom also. And using the space-time reduced order model, we were able to reduce that to 10 only, both in space and time. And as you can see from the movie, it's more or less doing the same dynamic, show the same dynamics. And quantitatively, the relative error was less than 1% if you use the basis dimension of 10. And the wall time speed up of around 30,000 was achieved. And again, if the space-time reduced model can only reproduce the full order model solution, that's useless, right? So in order to see the predictability, we have changed the source terms, the density of the air in the source terms, and from 0.05 to very small number, and we were able to see that our space-time reduced model was able to accurately predict all those variations. Although the local reduced model was built in this one point.
Youngsoo, I have a question on this because it's really interesting. we have something which you're working on. So what happens if you have multi-rate? Let's say in this problem you have reactions and they're multi-rate and you have a characteristic time of 1, characteristic time scale of 0.1 and 0.001. Which I mean, how do you deal with the time? Because obviously in the time space, you cannot take very, very long times, right?
Right. Yeah,
if
so
the time domain is big, and then you have also to resolve very small. That's a problem.
Yes. That's very good point. And although we haven't tried it, but I mean, there are a couple of options. You can combine this space-time reduced model with a time windowing approach I have just previously introduced, right? So you can think of, the time windowing space-time reduced model, where each time window you build a space-time ROM, and then local space-time ROM, and the division of the time window should be handled by will be depends on those multi-rates, the time stepping, and that's one option. And another option is just applying the space-time ROM all at once, as we did here, but there might be the variance time stepping which is inconsistent, giving us the challenge of the building a consistent temporal basis, because here our assumption is the data, the temporal data we obtained for each full order model simulation data is kind of consistent. So in order to address that inconsistency, we cannot avoid some sort of the interpolations and make it consistent, and then build the space-time reduced model in consistent way. I mean, consistent way, not inconsistent way. Yeah, so that's the two options I can think of for now. But yeah, I mean, that's, we have to develop further question. Yeah.
May I ask? Okay, my name is Pawan. So in this space-time, in this space-time decomposition, for finding this temporal basis, I need the data along the temporal direction as well. But whereas if I'm actually marching in time, I do not know my forward trajectory. That is what is the objective for me to compute it. So have I understood it well, or what are your comments on it? Because how do I compute the basis otherwise in the temporal direction?
Okay, so here we assume the final time is the same, for example, right? And also, I mean, for all those numerical examples, we use the uniform time stepping. So we don't have the challenges I just mentioned due to the adaptive time stepping. But if you are using the adaptive time stepping, but then you have to, you cannot avoid some sort of the interpolation to make the time step consistent. So I don't know this answered the questions or not, but other than that, I don't see any other. Yeah.
I still didn't understand it. I apologize. So let's say I have uniform time. My final time is 1 second, right? And I'm starting at an initial point. So I have a 0.1 second, 0.2 second, 0.3 seconds. So in order to compute this basis, I need actually the entire temporal trajectory to compute it, because this is the basis function that you're computing is purely data driven. So I need the data, but since I'm just starting my simulation, I'm at time t equal to 0. And I want to march in time. It's like time t equal to 0.1. For 0.1, I'm using some temporal scheme to go in time. But how do I compute this basis a priori? Because I cannot compute this basis if I'm integrating in time. That's my.
Oh, okay. So here, so for example, okay. So once you form a space-time ROM, the spatial degrees of freedom and temporal degrees of freedom is all integrated. And if you solve this, okay, so in space-time ROM, you solve this least square problem where the spatial degrees of freedom and the temporal degrees of freedom is embedded in this space-time basis, right? And the only thing you solve for is the coefficient in front of it. And this one solve of this least square problem will give you this the coefficient y hat, which presumably very small number of those are there. And once this is found, in order to reconstruct the whole space and time solutions, we don't relying on the time marching algorithm. We just simply plug this coefficient in, multiply that with the space-time basis, and reconstruct the whole space-time the solution span. So since you found the whole space-time the solution there, you don't have to time marching anything. I mean, it's analogous to the space-time, the full order model space-time the formulations, which is not popular in outside because it's its implementation is kind of cumbersome, and it's a lot of memories are required to solve the space-time the formulation. But however, it is attractable in space-time ROM reduced model sense, because this operator, after you integrate into the system operator, the size of the system the space-time operator becomes very small, and at the end you only solve for this coefficient which has like the small number of those. So it is very practical in that sense. And then yeah, so I think that answered your questions.
May I? Okay, I understood to certain degree. So I have the data in space and time, so I can compute those x's and phi's that x's and phi. What exactly is that coefficient y, y hat ij? What is that coefficient?
So for example, those are the generalized coordinates. So for example, in finite elements, the context you introduce the shape function as a basis, right? And then in front of it you have some coefficient, right? And in finite element solve, you're solving for those coefficient, right? It's directly analogous to that. Here, instead of the shape function, we introduce the space-time reduced basis as a basis, and then we are solving for the coefficient in front of it. So it's a kind of weighting of and then you linearly combine them to reconstruct the solution. So you can think of that. Think the coefficient as that way. Yeah.
Okay, but I can use your time windowing scheme to march forward in time. That would be pretty efficient scheme, because I already have a reduced basis in space. Then I can just go along in time with your non-linear or in your case of the time windowing scheme.
Yeah. Okay. Exactly.
So,
yeah.
One of my concern.
Pavan. Okay, let Youngsoo finish. At the end, you can ask the next question at the end. You ask 3 questions.
Okay.
Next one at the end.
Okay.
Please proceed.
Okay. Thank you. Okay. I think I have the last one to show, which is quite interesting also. It is a component-wise reduced order model lattice design algorithm. This is not the particularly a method of handling the advection-dominated problem, but I think it is it shows some very nice features. So that I would like to introduce that as your last topic. Okay, just to give you a motivation for that, despite all the successful story of the reduced model that I have shown so far, as the full order model size increases, the cost of the training becomes very expensive, right? And sometimes not even possible to train those because of the memory issue and etc. Right? And also a lot of the applications, the parameter tends to be spatially distributed. That is often cases in topology optimization. The applications where the parameter is the density variable, which is distributed over the whole space. So the high dimensional the parameter space causes the problem too, because the number of samples you have to collect the simulation data is exponentially increasing, so that it becomes intractable. Therefore, we looked for an alternative approach and found this component-wise reduced model pioneered by the Tony Petera's group at MIT. And here the method deals with the small size of the data because they deal with a small component, component by component, and they do the training on the component by component and build a component reduced model. And once you build the component reduced model, you assemble them together, just like a Lego block. And then once you build the system using those local reduced model as a Lego block, the whole system, the cost of the solving the whole system becomes low because you have worked out the reduction in your degrees of freedom at each component. So the total number of degrees of freedom will be reduced compared to the dealing with the whole system in monolithic way. And that technique, okay, let me skip this slide and then go to next slide. Okay, here, so here we are demonstrating, how we apply that component-wise reduced total model in the context of lattice structure design. If you think about it, lattice structure has very repeated component, so it's very advantageous for to apply this component-wise reduced model because you can build for example, this joint reduced total model and strut reduced model, and then using those only two components, you can make all sorts of the lattice structure, right? So let's, in order to explain that, I have to introduce very important concept called the reduced the ports. Okay, before ports, let's say you already, somehow are skipping a lot of details. Let's say we have introduced the joint reduced total model and strut reduced total model, the component wise already, right? And then somehow you have to assemble them. And here the important concept, the ports, has to be introduced, and which is an interface that talks to environments, and it connects with other component reduced total model. It can be used to impose the boundary conditions. And of course, you can add more components through an available port. It can be used to apply external force, and you can even rotate the component and attach to the system, and attach many more as you wish to form your desirable system domain. Then in design optimizations, in topology optimization, where the density variables has to be introduced, and which varies from 0 to 1, but usually we avoid 0 to ensure the well-posedness. So we set our low bound to be 0.01, and a small density variable 0.01 means you get rid of that corresponding the component, and the density variable 1 implies you put the material there. And we automatize, this procedure in order to find a optimal the density variable, like overall system, and we minimize, for example, compliance, and then introduce some bound constraints and also some mass constraints, like for example, from overall the system, you only want the 50% of the mass, in your optimal lattice structure, right? So those you can introduce that bounds, and then put that into the optimization solver. At the end, it's going to give us the optimal the density variable distributions, and it will give you this kind of optimal lattice structure. Okay, we have applied this component-wise reduced model to this, in numerical results. Here, the pressure force is applied on the top and the middle, and the boundary conditions are applied in the at the bottom. And then we ask only 40% of the mass should be, remained at the optimal lattice structure. And then if you run the optimizer, it is evolve, and by changing the density variable, and the red means density variable 1, and the blue means the density variable of 0.01. So only the red parts is remained as a optimal lattice structure. And we solve this problem using the monolithic finite element, and also the component-wise reduced model. And if we compare the speed up, we obtain like 660 times speed up compared to the monolithic finite elements. And as if we use the the static condensation type of the component-wise reduced model without the reducing the degrees of freedom at the ports, then we still get the 70 times speed up, and the accuracy can be tunable as you increase the more the reduced basis dimensions, and the accuracy increases exponentially, and so on. Okay, so that was the last example I would like to introduce, and this is my summary slides, and hopefully I have all those examples were interesting to you. And the examples I have shown you was the non-intrusive surrogate models for airfoil, and another the black box approach applied to 2D Burger's equations, and the space-time reduced the time windowing reduced model applied to the Lagrangian hydrodynamics, and the space-time reduced model applied to the Boltzmann transport problems. And also, lastly, the component-wise reduced model for lattice design, the problems. Also the nonlinear. Don't forget the nonlinear manifold reduced model, which I think has a good, promising features. Okay, with that, I'm eager to apply these techniques to many other physical simulations, and also because the here Brown University is the birthplace of the pins. I'm thinking about how to incorporate the pins method in the context of the reduced model. So yeah, so in that, I'm looking for the collaborations, and if you are interested in that, please. Let's do that. Let's do the collaborations. And that concludes my talk. And thank you so much for the listening.
Thank you very much, Youngsoo. That was an excellent talk.
Thank you. Thank you, George. I think it's exactly 10 a.m. right now. Oh, well, 1 p.m. in Eastern time.
Yeah,
right?
no, you're good. You're good in time. We'll have some time for questions. And Rui?
Yeah. Thank you very much, Youngsoo. And is there any questions for Youngsoo?
I would have one question with respect to the topology optimization. There was the error. Could you explain the error measure a little bit? So here's the relative accuracy with respect to what? So it's not the optimized shape, or isn't it?
Oh, well, I mean, although the final optimal shape was, given this red the figure, right? But when we measure the error, although this is blue is supposed to be gone, it's not completely gone. It's still there, right? And we compare the displacement fields as the error measure. So you obtain the solution of the displacement field from the Fluido model, and then obtain the displacement field from the component-wise reduced model, and then subtract it and take the 2 norm and square that. Take the 2 norm and divide by the Fluido model displacement, the field, the norm. So it's a relative error measure we are reporting.
Okay, thank you.
In this.
Yeonchon, Shin, do you have any questions for? I wanted to introduce you to Youngsoo.
Hi, Youngsoo. Actually, I haven't met him in person, but I requested him to follow. I did LinkedIn. Friend.
Okay.
Oh, okay. Okay, that's good.
You have any questions?
Yeah.
Yeah,
Nice to
thanks for
see
the-
you, by the way.
Yeah, nice to meeting you. Can you see my camera?
Yeah, we can see you.
Okay, great. Yeah, thank you for the very nice talk. Yeah, I have one question on your nonlinear manifold, the reduced order model, when you incorporate the autoencoder part, because my understanding is that if you want to get a good autoencoder, I think the deeper the network, the better the result. But I think you use some shallow network or 2-layer neural network to a 3-layer, so that is there some particular? Have you ever noticed that beside from computational cost, because the larger the network, the computationally expensive, but there's multiple ways you can use the deep network by reducing the width but increasing the depth. So that I'm wondering, is there some sort of like your empirical experience of how we design this autoencoder and your choice of activation function?
Yeah. Okay. So we of course, a lot of trial and errors was involved when we trained this neural network, and that was the most the immediate first step you have to accomplish. Your loss function has to achieve like around 10 to the negative 6 or 10 to the negative 5, the loss value. Otherwise, the performance of accuracy of the nonlinear manifold reduced model, even without the hyper reduction, was not that good. So that was kind of reference number we targeted, like 10 to the negative 5 and 10 to the negative 6. And then, as you said, we have applied many different structures, like convolutionally CNN with a deep structure. And so we did get pretty good accuracy there. And we also saw some, the robustness in the parameter change using the deep structure that was more robust than the shallow. However, unfortunately, even though how much we sparsify the, the deep neural network, as we increase the number of the hidden layers, the number of the involved hidden nodes to compute those selected outputs, this orange, was kind of increasing too much for us. So it was not just the evaluation of the neural net which bottlenecked the efficiency of the nonlinear manifold. It was the computation of the Jacobian of the neural net, because we were using the implicit time integrator, and we had to compute the Jacobian of the neural net. So because of that, unfortunately, we had to move on to the shallow neural network and sparsify it. And finally, we were able to get the speed up. By the way, this is ongoing research. Every time I talk to the reduced model group worldwide, they are working on this nonlinear manifold reduced model, because it's kind of hot topic in reduced model community, but they are struggling with obtaining the efficient hyper reduction with a deep neural network structure, because of the very reason I have explained to you. So it would be really ideal to come up with a method, some mechanics to still use that deep structure, and then incorporate that in the nonlinear manifold reduced model, but has not been found yet. And we are the first group coming up with actually the efficient hyper reduction using the shallow narrowed neural network. And at this moment, a lot of the reduced model groups are actively working on that, banging their heads on the wall. And
I see. And one more question I have is that in your formulation, you used some pseudo inverse, and I suspect that is probably because you probably get your metrics is most of the time is not, I mean, it's not full rank, but technically, if you fixed your reduced the dimension size, what we want is the full rank matrix, doesn't it?
Full rank matrix. Okay, the pseudo inverse. Let me try to.
Maybe I misunderstood something.
I skipped a lot of details because I tried to squeeze the many materials in 1 hour of talk. So it's my fault. Don't be okay. So the pseudo inverse shows up. Okay, here it's just the inverse, but pseudo inverse shows up because of the dimension of this matrix. So let's say you have the basis size of 5, you know, and so that. So you will have the column, the number of column being the 5, but the number of rows determines by the number of sample points you choose in the hyper reduction. So if those two numbers match, then you will end up getting the square matrix. So you can apply the inverse. But if you have more in practice, a lot of times we tend to include more sampling points than the basis size. So this matrix becomes dense tall matrix. So in order to invert that, we use the pseudo inverse, and that's kind of necessary to use the pseudo inverse. And there's just some stability, the issue going on. If you have the less number of sampling points than the basis size, then your problem becomes ill-posed. So the accuracy will degenerate like very rapidly.
Yeah, I think I remember the one of the slide you show some Galerkin versus Petrogalerkin update part. I think they have in that part you apply the autoencoder.
Here.
Yeah,
the pseudo inverse here.
Yeah, here. I see. Okay.
Yeah. So that's that can be inverse, but it depend. Most of the times we apply some more the sampling matrix, more sampling points than the basis. So the pseudo inverse is necessary. But as long as the number of sample points is more than the basis size, it becomes a stable, and the pseudo inverse is okay, numerically okay.
I see. Interesting. Okay. Yeah, thank you.
Youngsoo, thank you. I have let me ask one question, which talking about collaboration. So I have Muri, and I work with Charbel Farhat, who has his own ideas, and we invited Kevin Carlsberg to give a talk also, and all these people. And and of course you mentioned Tony Patter, and thank you very much for mentioning, because he actually started all this parametric, and people don't give him enough credit. He's my advisor, so I should speak up for him, because he's very humble. But he actually did a lot of work on this component and this parametric, including the empirical interpolation. But my question is different. In all these people, all these groups, great groups, and so on, the question is always speed up and versus accuracy. But actually, the new question that we are asking these days is generalization. In other words, when you come from the neural network, the first question would be generalization, because neural networks automatically can reconstruct very accurately what you give them. That's not an issue, even for very close by conditions. So I think what I would like to test with you, let's say with your space-time reduced order model, I would like to have a really kind of systematic investigation and honest investigation of, if I compare DeepONet, which is an over-parameterized network, expensive and so on, and I versus the space-time, which I think is very appropriate, and we can do it from molecular data, we can use like SPH data, we can use from continuum data and so on. And so we're going to have three metrics. One would be the speed up, actually multiple metrics: speed up, accuracy, generalization, how far from the baseline point, the base point that you mentioned, you can be and still get what accuracy.
Right.
But I think generalization should come in because that's really the most important point that we are struggling, as you know, in these whole applications. Because and another metric, actually, recently we introduced two new metrics for DeepONet, and that is the ratio of the training cost versus generating the data. Let's say you generate the data and then you also have to train and so on. So there are other metrics that one has to introduce. But let's say for now, we really need to introduce a generalization metric in the entire research on reduced order modeling, and also for pins for that matter, and DeepONet in particular for me. So I see a very appropriate race between space-time ROM and DeepONet. So we can carve out problems if you're interested in that to check it. Myself, I'm very curious about it, actually.
Definitely. That would be wonderful. And are you thinking about some sort of, I don't know, if you restrict to DeepONet and the space-time ROM, and maybe somehow we can combine those two, then if you can combine those two, then that will be a separate journal paper. But if you just compare those, the comparison, then that might be some sort of the.
I'm not talking about papers. I'm actually interested to see, let's say, for your Berger's equation, right? If I introduce initial conditions from a space like a Gauss random fields, and I change correlation length from 0.001 to 10 to 1, above 1 is the same. And so I build the input space, and I want to see now we are inside the space how well we're doing, outside the space how well we're doing.
Yeah, exactly. That should be.
So we can define things like that, and again, we can do that for continuum systems, and we can do that for molecular systems. So anybody who's listening and he wants to contribute, please send your ideas, because I think that's something that papers will come later. That's not the issue. The issue is like what is, because I think from my experience, that is something that is lacking. A lot of people claim victory for, and then use these local models like you described them. These plots that you show the blast energy are very telling, actually. They're very, very useful. And we have similar in our DeepONet when we did for the bubble. We have a very similar set of plots where we're looking at one correlation length, and second correlation length, a range of correlation lengths, and how much inside and outside that, of course. That has to do with the resolution that the Fourier net people, Andrew Stewart and so on, also are talking about. How can you be resolution independent? Here, resolution is not so much as you can think of correlation lengths, of characteristic length scales and time scales. That range you have, that's important.
Right. That sounds very interesting. I'm very interested in the comparison. Yeah, I'm in it. Please count on me.
Right. Thank you very much, Youngsoo. Thanks for taking the time today to show us all the great stuff going on in Lawrence Livermore. Maybe Andrew, you can continue.
Yeah.
Thank you.
Yeah, thank you very much, Youngsoo, for this great talk. And our next speaker is Amir Behjat. Amir, are you online right now? Maybe you can turn on your.
Yes.
Hi. Yeah. So Amir Behjat is from the University at Buffalo, and he is a PhD candidate in mechanical and aerospace engineering. And he got his degrees of Bachelor of Science in Mechanical Engineering and Master of Science also in mechanical engineering from Sheriff University of Technology. And currently he is working under the supervision of Dr. Soma Chowdhury with research focuses including heuristic-based optimization, neural evolution, and physics-infused machine learning. So today, Amir is gonna present a talk with title Physics-Infused Machine Learning and Evolutionary Learning Approaches to Design Intelligent Robotic Systems. So let's welcome Amir for his talk. And I think, yeah, you can share the screen.
So can you see my screen?
Yes, we can see that.
Okay, thank you so much. Hello, everyone. My name is Amir Behjat. I got my PhD from University of Buffalo. So I'm really honored and I'm really grateful for this opportunity to be here and talk about my research during my PhD. So my presentation is about physics-aware machine learning and evolutionary learning approaches to design intelligent system. So this is part of the works I had during my PhD. So part of them that could be listed and was more correlated to this talk, I just listed them here. And here's the outline. I start with a small introduction and why this problem is important for us to solve. So definitely this is a group of talking about data-driven models, and everybody knows their importance, and everybody probably knows the problems that we have with this data-driven model. They are data hungry, they are not sometimes generalizable, they are not robust to noise, and sometimes they are not easy to be interpretable. And in order to solve this problem, we are working on having efficient learning, making them more flexible, making them more transferable to new tasks, and using new tasks, instead of using the new task samples, be able to use the last task samples that we have to train them more efficiently. So these are the problems that we are solving. And in order to solve them, I list 3 different approaches that are partly used for this goal here. So first is physics-aware machine learning, that we are trying to predict the states optimally using physics or expert knowledge. Neuroevolution, which is used to make the optimal decisions, and we are using the GA literature to make it more optimal. And co-design, which is the design of morphology of a robotic system. And here we are using the control theory to make some prediction of learning capacity. I explained them one by one. So let me start with physics-aware machine learning. There are multiple papers we have, but I list these 2 here, which is more correlated again to this talk. So as just a background, this physics-aware machine learning is probably not new for people in this talk, but just as a small introduction, we have data-driven models which are computationally efficient for us, but they have generalizability issue. They have not easy to predict outside of the distribution of the samples we have for them in the training process. And sometimes they don't even follow the right trend when they're doing the prediction. On the other hand, we have physics-based model, which can be some partial model, which we can say they capture partial of the truth of the results, and they are simplified and computationally frugal. But on the other hand, their predictions are not accurate for us. And we have high fidelity samples, simulations that we have, for example, the CFD simulations that are very accurate, but we cannot rely on them because they are expensive, or sometimes we get the data only by the sampling and doing some experiment, like doing the beam tunnel and stuff like that. So what we are trying to do is we are trying to make make ourselves less relying on these high fidelity samples and use these partial physics samples that we have as much as possible to make the total model more accurate. So this is the main idea, and I'm sure that this is not something completely new for you. But this is the work we did, and this is the work we did in the with the support from DARPA in Physics of AI program. For this work, I had the chance to work with Dr. Rahul Rai from Clemson, Dr. David Duerman from University of Buffalo, my advisor, Dr. Choi from University of Buffalo, and Dr. Jan Mate from Park Company, Xerox company. So this is a very small introduction and literature about this physics-aware machine learning. The taxonomy of these different architectures can be categorized in 3 different categories if we look at a very broad view for them. We can have sequential architectures in which they use the physical model, this partial physics, this computational frugal model output as features to a data-driven model that we have here, and then totally we make a prediction based on all of that. We can have parallel model, which we have a data-driven model, and partial physics, and the output is somehow combined with both of them. How we combine them is different based on different architecture. But the point is that the outputs of this data-driven model and the output of this physical model just combine in the last stage. And we have some constraint data-driven model, which are very interesting model where we have a data-driven model to make the prediction, and the physical model is used to make the loss function align with the partial physics. So in some way, the partial physics is considered when they calculate the loss. So all of these models are good, and definitely we are not trying to say that what we are trying to do here is completely optimal every time. But what we are trying to say is that let's look more about the source of error. Let's look a little more about the physics here, even when we are making the architecture. So if I look at about the source of the error in this partial physics that cannot capture the full physics model, then we can have an idea of when and how we can use this data-driven model and partial physics model. Also, we can talk about the situation that partial physics and full physics operate in different space, and the ways that we can use the partial physics more and more for our modeling and increasing the accuracy of our model. So based on these ideas, we came with this architecture called OPTMA, which stands for Opportunistic Physics Mining Transfer Mapping Architecture. I explained what it is. So the main idea is that we were looking about the correlation of the input between partial physics and full physics. I explained what does it mean in next slide, but just as the information, this is the idea we had about the source of error. So we were looking about what is the source of this error we have. And what we want to do is to do something that the trend is actually at least followed by the total architecture. We have the data-driven and the physics together, and makes to an extent interpretable predictions, and it has good performance. So in order to do that, our idea was to use the partial physics as the last stage, because in the end, at least this partial physics can keep the trend for us when we are doing the prediction, and the results are not going to be far from the truths, because at least the trends that the partial physics dictates to the system can still be used in this prediction. And in order to train them, we defined backpropagation equations, and we designed a gradient-free training. And we tested it on some regression problems and some dynamic systems that I explain in the next slide. So as a very, very, very broad view, and if we want to simplify the model, we can think of if the data-driven model was a neural network, how could we use the partial physics? So again, this is not necessarily limited to neural networks as the data-driven model, but if the data-driven was a neural network, what could we do if the partial physics could be modeled as a extra node? So we have ReLU, we have Tannis, sigmoid, and let's just use this partial physics as extra node compared to the time that we have in sequential hybrid models, when the output of the partial physics is considered as extra feature and the original inputs are the first features we have. So let's see how can we solve this problem and use the partial physics as the final stage. And in the right, we see how its loss is calculated. The initial input is going to this transfer model, which we call it OPTMA. And then the transferred input goes to the partial physics, and the prediction is going to be calculated, and we compare to the full physics and calculate our loss. So this is how we are going to calculate its loss. And based on this, and by the assumption that we are using neural network, which is not necessarily the case every time, we can derive the backpropagation. So if we look at the loss function can be calculated here as the second norm, and some regularization terms for the weights. So if we consider this loss function here and we take the derivative of the partial physics with respect to transferred inputs is going to be part of our error signal. And then we can use this new error signal instead of our original error signal and then backpropagate it, which is actually a good method, and it's working, and it's working fine for the large networks. But the issue is that sometimes this partial physics itself has is multimodal, and the answer is going to be stuck because of the multimodality we have in the partial physics. And also, sometimes the partial physics is not easy to make the differentiation. For example, a dynamic system and solving an ODE different time steps is itself a partial physics for us. And therefore, it's not necessarily easy to get the derivative back. So another approach we can have is to have a gradient.
Amir, can I ask you a question? Amir, can I ask you a question? Because
definitely, Professor.
I haven't figured out what language you're using yet. Are you using engineering language, mathematical language, or computer science language? So when you say multimodal, what does it mean? In the statistical sense?
Yes, Professor.
Or do you mean multi-scale? In other words, if I have a Helmholtz equation which has like megahertz, is that multimodal, or is it although deterministic, or is it I have two Gaussian bumps? What do you mean by multi?
We have more bumps, Professor. And then the gradients is going to be 0 in many places, or we can have sharp gradients and makes this loss function, this error signal, harder to backpropagate.
So you're thinking of the loss landscape.
Yes, Professor.
Okay. All right.
Thank you so much.
Hi, Amir. I have another question. Sorry.
Definitely.
So maybe I missed something, but could you explain what do you mean by like partial physics here in this context?
Yeah, partial physics, if I want to give an example, actually I had the examples later, but if, for example, I want to give an example, think of when you are modeling, for example, air flow over a A4, okay? So you can have a CFD model, or you can have just a simple, a simpler model based on the, based on X4, based on the, what was the thing called? Based on just give you the example here. Based on the potential flow. Yes, sorry, I forgot. If you have something based on potential flow, so you have a model that is computationally very fast to calculate it. For example, the potential flow model. But it doesn't have the higher accuracy compared to the real data you have. And you have a model that is very, very accurate, but it's computationally not so easy to calculate. Is it the question you have?
Oh, yeah. Okay, yeah. So so here FPP means that
partial
the variable, the variable for your sort of reduced order or simplified system, right?
Exactly.
Okay, yeah.
True. Yeah.
Thank you.
Thank you so much. Okay, so if we want to use the gradient-free training, we can use different solvers. I used PSO and also use CMAES. And here we can use just the weights and the biases as the parameters that we have in this neural network and just directly optimize them, which is good because the population-based methods do not have as much as problem of stacking local minima compared to this gradient-based solvers, but they are not scalable. If the network is increasing, the size of network is increasing, and this is something may happen based on what we are facing for the problem and what we require, then using them is limited because these solvers cannot work well with this large input sizes. So that was the way to solve it. And actually, for this initial results that I show you, I used the gradient-free one in order to avoid that. But I also used it with gradient-based solver for another problem that I explained. But here is just an example of where optimize is useful. So this is Gram-SC and Lie function. It's a problem that is used as benchmark problem for optimization method usually. So what we are trying to do is to make a case for ourselves in this partial physics and full physics modeling. So assume that we have this red one as our partial physics, and we are testing how can we use it to predict this green and blue one, which are our full physics question. So if you look at these two problems, the green one doesn't have any correlation. It's output for the red one. So the output is completely different. They have different modes and different maxima. But the input is actually very similar. Its input is almost flipped. On the other hand, the blue one has a good correlation of the output, but the input is not that much correlated. So our hypothesis is, if you are using Optima, the green one is the one that's going to be benefiting from that, while the blue one is not going to be benefit from that because there's not any input correlation here. And the results also show that. The results shows that if you're using with this green one, which is the first one, the Optima is performing much better than the other methods, which is pure data-driven and sequential when we're using the output of the partial physics as extra feature. While we're using the second one, this blue one, the performance of Optima is becoming worse and the other methods are becoming better. So it shows that there is a space for Optima to be used, and that space is that is where the input correlation is strong, while the output correlation might not be so much strong. So that was the problem. I explained it just to show where and how it's going to be useful. But the problem that the other problem that I'm explaining right now is the one actually we promised for DARPA to solve, and that was the predicting the UAV trajectory and collision avoidance of UAV. So as initial stage, we wanted to just predict the UAV trajectory. So assuming that we have a UAV trajectory, this red one, which is not affected by the wind. And what happens if the wind is going to affect it? This blue one is going to be the actual trajectory is going to fly. So what we are trying to do is to predict this blue one based on this red one and just these architectures we have. So here we have two ideas. One idea we call Optima Edge or Optima hardware. We are considering changing the hardware parameter. So what we mean is what shape of UAV, mass, arm angle, and arm size could be there that if it faced this real trajectory, real effect of the wind, it partial physics generated the same output as the full physics. The other idea is that instead of changing and deforming this UAV, we just change the thrust of each motor. So what thrust in each motor could be used that when we are seeing this wind that we didn't consider during our partial physics, the partial physics output generate the same prediction of this actual physics. So we call this one Optima T, which is for the thrust of the motor. And our hypothesis here is that this one, Optima T, should perform better because there's a clear correlation between the thrust of the motor and effect of the wind, because effect of the wind is going to generate air drag, and air drag is going to affect the forces and acceleration, which is easier to model using just the thrust of the motor. And the results also approves that. The results approve that when we are using this thrust, Optima T, the performance is better than Optima Edge and also sequential and pure data driven. And more interestingly, if you look at the different sources of error in X, Y, and Z directions, Optima T's error in Z direction is much smaller than Optima Edge, which means that because the height of the Z direction, the position in the Z direction, is more affected by these forces generated by the thrust of the motors, the error in that one is smaller. It could be modeled much better compared to the time of the X and Y directions, which is again showing a very important thing here for us, that choosing these variables that we could use hardware or we could use the thrust of the motor is important to get better prediction. And this is a question that we are trying to solve and find a systematic way compared to this one that we just handpicked them. Systematic way to find what parameters we should transfer. Okay, so after that one, we expanded on using Optima in different problems. So here is a problem we submitted in aviation conference. So the idea here is that if you look at, for example, to sharks, shark skin is not smooth. Shark skin has some riblets, some small riblets, that helps it to decrease its drag. So what we were trying to do is to design some airfoils with some sigmoidal shape riblets that have three parameters, H, S, and sigma. And based on these three parameters, we were trying to predict the drag coefficient. So we had CFD runs that took 16 hours, but we could also use the potential field using Xfoil that could take 0.4 seconds. So there's a clear computational time change here. And what we were trying to do is that we wanted to use these predictions in conjunction with data-driven model that here was GP, not neural network. And in a Bayesian optimization framework, make the optimization of this airfoils and this riblet more optimal. So what we did is we compared the results. First, we just used the GP model, then we used the Optima GP model, which is using the Optima in conjunction with GP, partial physics in conjunction with GP. And the results are better. The error is actually very small, about 0.5%. And more importantly is that these errors are really what matters in drag coefficient, because drag coefficient reduction is not a very very significant numbers many times, very large numbers many times, but still it's important because it costs so much for aviation companies to have less, have higher drag. And this is actually the main source of their energy consumption. So one other thing that I want to say, that compared to the last results that we chose the samples in the same distribution of the training, here we are using extrapolation. So the test samples is not the same distribution of the training sample, which means that Optima could use for extrapolation and could be used with different models like GP. The third example that I'm explaining is a bipedal problem. This is one we have just initial results, so I don't go so much in the detail. But the problem that we were trying to solve was designing a robot to walk. So this robot that tries to walk, if we consider partial physics, means that the estimation of the states is accurate and the motor torque is generated the way that we want, it can move successfully, making 8 steps, for example. But when we are considering the full physics, when they have some errors in the estimation of the states and we have some deficiency in torque in the motors, it falls. So what we are trying to do is to predict this fault. So this one is a classification problem. And we used Optima, just compared with the deep neural network here. So initially, the results were almost the same. The accuracy of the Optima data-driven model was the same. But then when we added 10% mislabeled data, the results of Optima become so much better, which shows that it's robust to noisy data. So if the data is not accurately labeled or there are some error in measurements, here is a little hard to imagine because of classification problem. But in general, if there's error in the model, it's better to keep the partial physics in the loop because it helps us to not follow a very wrong trend. And this is actually the initial result. I say this is not so much still developed. One other thing is different here is that instead of using gradient free here, we use back propagation. But in order to do that, we were forced to make a DNN initially to just train the, to just model the partial physics with the assumption that partial physics is something it's completely free for us to evaluate and we have infinite number of samples. So it's not wrong to make a 100% accurate with thousands and hundreds of thousands samples for that. But the full physics is something that we don't have. We should get it either with high fidelity simulations or just experiment. Okay, just another example that I have here is something we submitted to JASA, but I don't go to the results because this one's result is not still reviewed and I cannot say it's come perfectly fine or not. But the importance for this example for us was that we are using experimental data. So we are using a Vicon room. We had Vicon cameras to look at the location of a UAV, and this UAV was flying. So the idea was to measure the noise that the UAV generating, mostly for people who were working, for example, for Amazon or other places that they plan to use the UAVs in addition to the human for employees, and they wanted to see the effect of the noise on them. And we were using this mechanism to move these microphones and calculate the sound pressure level. We calculated that and made some low filtering thing, which I didn't do the low filtering thing and calculation, so I must give the credit to the students for Dr. Nu in University of Buffalo. But what we were trying to do is to make the prediction more accurate compared to what they have. And the idea was to add a low fidelity model, the partial physics model, which was the ideal isotropic pressure distribution. So there's are a lot of things affecting this sound pressure from this UAV, including the shape of the UAV, room, and other stuff. So the idea was what happens if we just use the prediction without any other sources of the error here, and then use this data-driven model, data we have to make the prediction more accurate. So this was the problem that we tried. And finally, there was another architecture. So as I said, this was a joint project with us in University of Buffalo and Park. And also there are multiple professors that involved here. So this architecture is not something that I made, but I was also in the paper, so I just mentioned here. So it's actually a sequential architecture. We have a partial physics model. And what we do is that we are using different inputs and the outputs of the partial physics and cascade LST models and make the final prediction. The part that I have in this project was mostly about the samples and making the model. So we made the ODE-based equations for cancer growth, avascular tumor growth, that uses the idea that we have some stem cells, they have a symmetric or asymmetric division, and then we get semi-differentiated cells. And semi-differentiated cells, unlike stem cells, they have limited age. If they differentiate, they get less differentiation possibilities in the future until the time that they cannot differentiate at all. So based on this idea, we came with different equations. So these ODE equations are here. And these ODE equations shows us what is the total size of the tumor after some time in T. This is our partial physics, which is computationally frugal to calculate. On the other hand, we have a cellular automata model based on Polzak and Enderling model. So this model that we change it a bit to make it useful for ourselves is using the same idea, but it's a discrete space model, and the cells are growing based on some rules, and also the presence of glucose and other important vital resources for them to grow. So the cellular automata, which is more complex one, was going to be predicted using the partial physics one. I don't go to the details of this one because I didn't generate the results, but the results shows that the hybrid models, which is PySTM here, works better than pure data driven. So there's a scope of this kind of applications too. So as a conclusion, this was an architecture we designed to map the input space from the partial physics to the full physics, or to the latent space in the full physics when the variables are different. And we derived the backpropagation and also PSO gradient free optimization. And also we tested on different problems, including the UAV prediction and surface flow problem that I explained for the riblet design problem. Now for the next step, I'm thinking about having the momentum in a way that helps the backpropagation. We have some backpropagation results, but this backpropagation results can still be limited because the actual partial physics function might be multimodal or might have sharp gradients that even full physics don't have them, but still it's going to hurt us when we're trying to train it in gradient-based method. And another idea is to find a systematic way to find the optimal transferred inputs, which we right now using hand-picked domain, based on the domain knowledge. So this was the physics aware part. The next part I'm going to explain is neuroevolution. So the idea here was that we were trying to make physics aware machine learning to make, for example, that optimal UAV trajectory, and then use neuroevolution to, for example, learn collision avoidance for that. I don't go through the collision avoidance part here because it's taking so much time and it's a little out of the context here, but this was how these two projects were correlated and related to each other. Neuroevolution itself, what is neuroevolution? Neuroevolution is you training neural network using GA. Definitely we can train the weights using GA, but also we can do something much more interesting, and it's training the topology of the network. So in the left side, we see the output of our architecture here, our framework here. And you can see this network is simple, it becomes more complex, and it doesn't have a layer structure, it has a very, very strange structure compared to normal networks. And that's what GA can do, and backpropagation cannot easily do. It's useful for us because it removes the requirement of doing hyperparameter tuning and network topology tuning. Also, because we can work with the smallest possible network, we don't have the problem of we don't have the problem of overfitting and underfitting. So it's totally a useful approach when we are trying a system, especially for RL problems it's used. So I go a little about the literature. I don't go over every possible architecture we have in neuroevolution, but the most famous ones are this NEAT, HyperNeat, and ES-HyperNeat, which is stands for neuroevolution through augmented topologies, and they are coming from the same group, obviously, and they are very famous and very well known, but they have limited control over nodes that if I want to explain, is that they are encoding only the edges of a neural network. They are not controlling the node activation or how the node can be used for ODE equations. There is another architecture, Suna, which is a good architecture. It also has a very interesting speciation, but it relies on mutation for its optimization, which is limiting because without using crossover in GA is not going to be very different compared to a intelligent random optimization, so random search. So we have this issue for Suna. And there are hybrid methods which are very important, but they are mostly as an add-on to the other architectures that they use deep learning and gradient-based in conjunction with neuroevolution. So many times, for example, they train the topology using neuroevolution, and then they do some nested gradient-based optimization over the edges, weights, and biases to make the total network more optimal. So based on this, problems that we saw and how we could actually improve them, one idea was to improve the node control, but the most important thing for us was premature convergence and the loss of the diversity, or just relying on pure randomness, which I explain more. So we came with the architecture we called AGENT, which stands for Adaptive Genomic Evolution of Neural Network Topologies. So what is going to be done is actually trying to use the selection pressure and reproduction operators, mainly mutation, to resolve the stagnation and diversity issues. And in order to make the training more computationally frugal, we had an issue with NEAT that it starts with the simplest network, or it starts with a fixed network. And the idea was to find a method to speed up this thing. And for this one, we wanted to make the mutations to be able to complexify and decomplexify the answer. I don't go through the GA operators that we define here, the crossover and mutation and speciation, because that they are mostly in the paper. But I mostly go through this adaptive part that I explained, and we tested on different problems. So this is the architecture of the agent, and deep in its heart, it's just the GA. It has encoding, population optimization, speciation, selection, which is a tournament selection, crossover, and mutation. And they have some elitism here using some additional more GA operators here. But the parts that we are adding mostly is this adaptive mutation and selection pressure. So diversity is something we want to control. Anybody in a population-based optimization knows that the diversity should be controlled. Sometimes people try to keep it. Sometimes people try to gradually decrease it. But anyway, if we have a desired diversity, we must be able to control it. Improvement rate, on the other hand, is a little counterintuitive because originally it's what we want to do is to improve the best answer. But in reality, if when we were using NEAT, we faced that if we are using just improving the best answer, when the population becomes so behind the best answer, it cannot improve the best answer too, because the crossover and is going to lose its value because the other population are so bad. And everything that we can rely on is just pure mutation, which is not a good idea. So we try to control both of them. I don't go through the depths of these results, but we have some empirical evidence that it shows actually in controlling them are useful. So how we want to do it? First, we want to control the diversity, but before that, we should define the diversity. Diversity means the distance of networks compared to the other networks. So neuroevolution is GA over neural networks. So we have a population of neural networks, and we want to find what is the difference between them. In order to define the difference, we use this equation. So NT is the number of types of the nodes. So for example, we have ReLU and tanh and sigmoid. And we define this equation as the difference between network A and network B. So the number of nodes and number of edges from this respective node types. So this equation is very interesting because it doesn't have anything to do with weights and the output of the neural network. And this is because in neural evolution, we always give a more priority to the topology compared to the weights. We assume that the weights can be further optimized later, or even the mutation rates for them is higher. But the topology is something that we wanted to change slowly and fully exploited before we throw it away. So we always care about the diversity in the topology more, and we want to keep them in the population more. So how we are doing the calculating the diversity is that, okay, we have now the difference between the neural network. So we make this fully connected graph. So this is a fully connected graph, and each node in this graph is a neural network in the population of GA. So it's a fully graph, and each node is a neural network itself, and the distance between them is the distance we defined here. And we use the minimum spanning tree here using cross-color or any other algorithm. We use the minimum spanning tree as the representation of the diversity. So the total diversity on GA between this neural network is the minimum spanning tree that they form together. And finally, now that we have this diversity, we can control it. Assuming that we have DDT as our desired diversity, we can control it using the ratio between NW and NT. So this is using actually based on selection pressure. NW is the number of the winners in a tournament, and NT is number of participants in a tournament. So if we want the diversity to decrease, we allow less winners to the tournament size participants. So therefore, the bad answers, the low fidelity, low fitness answers cannot go to the mating pool and reproduce offsprings for the future generation. Same thing is for improvement rate. For improvement rate, we use the idea based on the changing the fitness compared to the last generation, and this can be the fitness of the best answer or the average population. If it's the fitness of the best answer, it's the best genome improvement, and if it's the fitness of the average answer, it's the average answer optimization improvement. So what we are trying to do is to keep this best and the average in the same rate. And if the best answer is higher, then we are decreasing the mutation rate. So we are allowing the other population to reach to the best answer using crossover and selection pressure. And if the best answer is not as good as before, and it's just like the average answer, we allow the mutation to be higher and it can explore the space better. So these are very, very nonlinear problems to control, but the control results shows that we could almost control the diversity. We wanted to decrease gradually, and we wanted the improved range of the best and the average answer to be almost the same. So it's relatively good controlled answer. And as I said, we have empirical results that shows that it's actually working. So after defining this algorithm, we tested an OpenAI problem. So actually you can see the optimization results of this mountain car here, original behavior from what agent could teach it. And we compared it with some published works in RL and also PyTorch NEAT. PyTorch also has a NEAT library. And in two of these problems, we were better, mountain car or acrobat, but in lunar lander, we were worse, performing worse than the RL algorithm, gradient-based RL algorithm. And the reason is mostly because lunar lander has discrete inputs and output, and lunar lander answer was not converged because the network size needs to be increased. And when network size is going to be increased, then the problem of training is going to be more and more for us. Because relying on GA to training a large number of parameters is hard, and it's not always optimal thing to do. Okay, the other problems we solved using neural evolution is for swarm robotics. So this was a joint work between different groups, computer science and mechanical engineering, University of Buffalo. And we working for DARPA offset program. So offset program for DARPA was trying to find tactics, learn tactics for a heterogeneous robots team to do some missions. For example, this mission was to find the target from different possible location, rescue it, and also there were some enemies, smoke, some bombs, and things like that. There were different aspects. We had high fidelity simulation. We also went to the field for hardware implementation. We had some human imitation learning, and also we used the EEG signal of human to find what part of information is important. But the part that I worked mostly was learning and encoding. So the question that was here was how to encode this large number of robots that also were not constant, and the map also was changing every time. So we were always seeing new maps with the enemies that are not seen. So there was a stochastic problem too, and how to deal with that. So in order to deal with that, this is more a practical problem actually. So what we did is that, for example, we had this Google map picture of the environment, this urban environment that you're trying to learn tactics for it. And then we made a graph representation of that using this abstraction of the map to a graph shape that we have using important points. And then for the UAVs and UGVs, the robots we have, instead of considering their states, we consider clusters and the central affairs clusters. So this was the first step to limit the number of the robots. I mean, keep the number of robots changing, but still we keep the same dimensionality for our input. But how about to define the states of this robot to this map? We came with the idea of Pareto front for multi-object optimization. So if you look at this map in the left, and if you just look at some small part of it's actually rotated. If you look at the problem as finding the target in these two different points, if you look at these 2 points, the point in the top is more optimal for us because it's closer to both targets. And for example, this point still is good because there's a target here that is closer to this one. So if you look at them, these points are non-dominated if we consider closeness to the possible target as our objective function. So non-dominated points are the interest points for us. These are the only points where we find the clusters based on them. And in order to keep the number of them limited, we are using this crowding distance idea from NSGA. So here with this idea, we kept the number of the points and the clusters fixed, and we are able to make the states, number of states fixed for every possible map and every size of robots that we have. And the output part is we are defining just a squad of the robot and where they go and how aggressive they should go. So if, for example, there's a time, and this is something that RL actually should learn. If there's a time-sensitive situation, they should make a higher risk and go through the enemy to the goal. And if there's a okay-ish time, they can make a smaller detour. And if the time is really enough and the robot team is small, we should make a bigger detour. So these were how we define the actions, and the actions can only be chosen from this Pareto front interest point. So by doing this and keeping the fixed number of squads, we made the number of actions also limited, also fixed. So this helps us to have a fixed input and output size, which helps us to make learning possible. And these are some of the results that we can show in some of the map how this simulation really works. The UAVs go, the enemies also go and reposition themselves. They encounter with our team, UGVs also going slowly, and they search different buildings, and they found that one building doesn't have any target and so on. And the results also shows that the optimization really helps. The average rescue time decreases, and the network also gets complexified so much. The number of layers increasing from 4 to 14, and the number of the parameters, which is the number of edges, and the number of the nodes increasing so much, which is very hard thing to train using neuroevolution. So that's the part that I think neuroevolution going to be limited for the future work unless we are adding those hybrid ideas. The other thing we tested was testing the...
Amir, can I ask a question here? What happens if I have 100 drones? It doesn't scale, right?
If you have 100 drones, Professor, if you have 100 drones, still if you use the same number of clusters, then the size of the input for us is the same, but those clusters are larger. so one of the parameters that defines our clusters, I didn't go through depths of what are the parameters defining them, but for example, one parameter is the size of the squad, size of the clusters. So those cluster size is going to be increasing, but the number of parameters we have is not going to change. And for the output, we are still defining, for example, 5 squads of the robots to go different places. So those are squads going to be consist of the bigger size of the robots. Everything here is normalized. So their actions and states are normalized by the initial size of the group. So for example, we still generate 0.3, means 0.3 of the total population should go to this special squad, but this 0.3 becomes 30 instead of 3. So that's how we can work with this one. But learning going to be harder, to be honest, because the uncertainty is going to be increasing for us, and that's my understanding. But and a simulation is going to be slower, definitely, but still we can hope that the same learned model can work. That's the biggest advantage for us. A lot of times that we were training this, we had multiple scenarios. We're doing some Monte Carlo sampling of scenarios. And in different scenarios, the number of robots, for example, changed from 6 to 30, or 6 to 80. So 12 to 30 and 6 to 30. 6 to 12 and 12 to 30 for UAVs and UGVs. And still it was working with the same model. So yeah, that's my understanding. The performance will decrease, but still is applicable. Did I answer the question or?
Yeah, okay, thank you, yeah.
Thank you so much. And we did some ablation tests of seeing the effect of encoding. So if we have the input encoding and output encoding, which is the cases we have in this optimization, the results are optimal. If we remove the input encoding, and as as the professor mentioned, we use every robot state separately, for example. The problem is not going to be scalable, but if we keep the size of the robots fixed, still we can apply the learning, but the learning performance is going to be a little decreased. But if we remove the output encoding and we allow the robot to go to any location, then the learning is going to be at least practically impossible to do, because considering only the interest points helps us to make the problems much more guided, much more actions guided to the right answer. So without the output encoding, the performance is almost impossible to capture any performance, and it's always mission failure. So as a conclusion, this agent was the method we used based on neat formalism, and also we made a diversity quantification using minimum spanning tree. We controlled adaptively mutation rate and selection pressure. And also we tested on different problems, including OpenAI problems and this swarm problem, which was the most complex problem. We used agent for that. On the future, I must work a little more on adding other architectures, like having RNN in here. The problem is mostly every time we add more complexity, then the deficiency of GA for training them is also being more visible for us. So we should come with some indirect encoding that can work with larger networks, but with limited parameters. In other words, it's just assuming that these weights should have some interdependency between themselves. So a smaller number of parameters should define a large network's weight, and that's the future scope of this neuroevolution. Finally, the part that I want to explain is about brain and morphology co-design. So this problem is actually more for design groups, in engineering groups, that assuming that we are trying to design a robotic animal, rhino and a cheetah are possible choices, and we wanted to make it very maneuverable. So we can construct them and we can apply learning on them, and to an extent they will both improve in their maneuver, but really we cannot expect the rhino to have the same maneuvers as cheetah. So it's obvious for us when we look at it, but sometimes we are doing this brain and morphology. Morphology means shape of them, hardware of them, together optimized in a cascade way. We train them, or we make the morphology, then we apply the learning and go on. So is there any way to predict based on just the shape in a methodological way that if you're designing something that looks like a rhino, it's probably going to be acting like a rhino and not a cheetah? So that was the question we were trying to solve. So the problem that we had was definitely not Rhino and Cheetah. It was a UAV, blended wing body UAV. And we were trying to optimize the shape, the propeller, arm, and the motors, for example. That the goal was here to make it able to fly, take off and hover, and also have the highest range of the flight, for example, if it's going to be a UAV that's going to use for some delivery targets. So initially, we had this one submitted to aviation first without this idea that I'm explaining right now. And this was the framework we have. I don't go through this framework. I blurred it with this goal, but this is the more complicated one, and it has a lot of internal loops. One aspect of this that's important is the learning capacity. So we should be able to estimate the learning capacity of the morphology. We should say that, okay, this robot has this much ability to learn to hover. This unit can learn to this amount of the accuracy based on its own design, based on its own hardware and morphology. So what can we do? We can have nested approach. We can have a model fitting approach, which is a surrogate approach for estimating the learning capacity. And we can have a cooperative and changing from one disciplinary to the other disciplinary and come back. All of them are fine, but they are computationally expensive. Obviously, nested approach is the best theoretically, but with a 40 core machine, it takes 7 days to solve this problem to the level of the accuracy we want. So what we were trying to do is to estimate it with order of complexity of 1 instead of doing this nested approach. So what we were trying to do is to estimate if a morphology has a talent to learn. So how we want to do it is we wanted to use the ideas from the control theory. So this is assuming that it's a linearized system with A and B and C and D as the matrices that we have. And we can define the controlling matrix here with B and A and the powers of A. And if it is not ranked efficient, we say the system is controllable. But if we want to make a little more quantified answers, we must look at the controllogram, which is defined in this equation for this integration. And controllogram eigenvectors and eigenvalues tells us which directions are more controllable. So the idea here was, if you look at the controllogram of a morphology of a hardware, it doesn't require any learning to just get the controllogram. It's just what we have from the hardware shape and this A and B matrices. Can we predict what system is more talented to learn? So our goal was, okay, our goal was that to find out that, I explained based on an example that we have here in the right side. It's a UAV that tries to take off and hover. So our idea was this. The most talented system is the system that its controllogram aligns the most with the reward that it wants to learn. So definitely every system has its own controllogram, and there is a possibility for it to control some states better than some other states. And if you look at this reward function we have, and if we assume that a reward function can be defined in the summation of different terms with clear understanding of the states to control. So for example, here we are trying to control Z direction. It's not a linear function, but still we know that we are controlling Z, this third state in the system. Or here it is L, which is the X and Y together. We know that it's trying to control both X and Y. And it is velocity, we know that it's trying to control Vx, Vy, Vz. If we have this clear understanding of which direction the reward is defined, and we have the controllogram eigenvectors, and we have the controllogram eigenvalues, and we have the reward weights, then we can define this metric talent that tells us which morphology aligns the best with our reward, which morphology is probably easier for us to learn. So we tested this on the problem that I explained, the UAV learn to fly and solve the flight range. And we got some different answers. So what we did is we chose two of them, answer 1 and answer 4. Answer 1 was also optimal in some aspect, and answer 4 was optimal in other aspect. And we compared and we applied neuroevolution, the agent to learn. So these are the optimized network, and this one is a little more complex. And then we looked at how the learning actually happened. And we see that actually the hypothesis is to an extent true, and the one that we defined using higher talent can learn something better and can control his height as we wanted in 10 meter compared to the other one. So still its initial results is published, but still its initial results, and it has more work to do. But it's a promising results for us. And as a conclusion, I wanted to say that the framework that we design here is finding talent to find the control-Gramian and find the most learnable architecture. And the results are still initial stage. It's promising, but still initial stage. And this linear combination that we have for the reward and the control-Gramian eigenvalues and eigenvector might not be very optimal way to model the talent. And also, if the reward is not defined as these terms and weights, for example, we have a sparse reward like end of a chess game, how can we further extend this architecture to use that? So these are the future work we have. And finally, I wanted to thank the people who I had the honor to work in these 4 years and my PhD. Some of them left, some of them joined, some of them I didn't even met personally due to COVID, but I'm really grateful for all the things that they gave to me, and also my advisor, Dr. Shoma Chaudhry. And if there's any question, I will be grateful to answer. Just this is the UAV problem that I mentioned. Using both Optima and the collision avoidance problem, you can see how they avoid the collision. Thank you so much. Any questions?
Amir, we have undergraduates here, so you never mentioned what GA is.
I'm sorry, I apologize, Professor. GA means genetic algorithm, which is one of the possible approaches in evolutionary algorithm we have. And it operates mainly based on two different operators, which is the crossover and mutation. And it's inspired by the idea of the survival of the fittest in the world. It's a population-based way of optimization. This is actually most common, I can say, most common population-based optimization or heuristic-based optimization. And the origins are from works of Holland in 1970s, but still it's a active research, and it is very important because it can work well with the combinatorial optimization and categorical and discrete optimization, and also it's fine to work with mixed integer optimization. But I personally don't suggest using only GA for continuous optimization. It's not as efficient as other methods like CMAES and PSO, or using just gradient-based methods sometimes. So, thank you. Any other questions, perhaps?
Amir, I have one question. So also about the first of your parts about the partial and full physics model. So is that about like two different levels of models which have different maybe fidelities? Like one is more ideal and simpler, and the other is more realistic and more complex. Is that correct?
That's completely correct. Yeah. So if I want to give an example, yeah, here is these two models. The CFD model is more complex here, and the simpler model is this X4 model. Just one other thing is that sometimes the high fidelity here means, or the full physics means just the samples from experiment. So for example, in the problem we had for this UAV noise, the high fidelity is not a simulation itself. The high fidelity is just real data. And that's the most important part, because we can still say, okay, we have cloud computing, we have this kind of capabilities, and they are rising. So we think that our requirement of this kind of method is going to decrease because we can have better simulators. But sometimes the real data is just experiments. Sometimes the real data just comes from the observations that cannot even be called as an experiment. You have some astrological thing. You just see it once, twice.
Amir,
yes, Professor.
How is this different than the Shuhui, who is listening, is a postdoc, and he has written a very popular bestseller paper in JCP. It's called multi-fidelity pins. So how is that different from what you're saying?
Yeah, I didn't read that paper necessarily, but about
this is exactly what it is. It's sort of it explores the correlation between different fidelities. It has sometimes, like you said, you use the high resolution or experiments we use. You know, this is just different. I mean, for the first part, I couldn't follow all the stuff that you did with the GA because I'm not a GA person. But the first part with the partial physics and partial, there's no such a thing as a partial physics. It's always the same physics. It's just that how we observe it. So it is really the fidelity or the modality that you're using. So you're talking about multi-fidelity in some hierarchy that the user defines, and then and so on and so on. I find this this work. I couldn't evaluate actually what you're doing because it's at such a high level that I couldn't tell what's the technical contribution here. Because we've been doing multi-fidelity. To go back to our GP, I think with more than I did co-Kriging 20 years ago, but that's different, but kind of similar.
Yes, yes.
But so I couldn't tell. That's why you hear all Min Lang and all the people are asking you questions about partial physics, because we call that fidelity, how you observe the physics. Physics is always there, the same.
That's completely true.
So can you sort of point out what is the new thing that you did here?
So the way that the thing is new is that how to use that one, how to make it inside the model. So if we
let's see your loss function.
Sorry.
Let's see your the loss function. The loss function, yeah.
Yes. So the loss function itself is the prediction, the same thing we have as a loss function. But for example, what we are changing is how to use the partial physics. One thing actually you mentioned, compared to the physics-informed models, there's a difference here, I can say, that we are using the partial physics more explicitly compared to the implicit way.
Well, define for us, give us the Berger's equation that the previous speaker was talking about, and tell us what is FP for your Berger's and what is FPP, or for the airfoil. Tell us what is FPP, because F it seems to me like F is a, is it a functional? Is F a functional?
F is just a function. So for example, let me.
How could it be a function if it's it's a function of data points?
Yes, exactly. It's a function of data points. So here in this one problem that I have the equation, the FPP is this equation. FP is this equation.
Right. So that's we call that multi-fidelity. So your red is low fidelity, and that's a data. That's pretty simple. That's actually very, very simple.
That's true.
So what you're showing me here is really trivial. We call it, if you look at the paper, we call it a pedagogical example, which I think is your example is pedagogical. But I want to know what happens if you have let's say flow around the airfoil with riblets. You don't know that I was the very first to do DNS of riblets about 25 years ago. DNS, RANS is not correct, but anyway, never mind that. Tell us here, what would be the partial physics? Because already RANS I call that partial physics.
That's completely true.
Okay,
yeah,
so what is
No, let me explain. If you look at in different perspectives, sometimes it depends what kind of what level of fidelity you want from the total model.
But I want to ask you a question. You already spoke a lot, so I want to ask you specifically. Go back to the loss function, and for this problem, define for us what is FP and what is FPP.
Yeah. So I'm sorry. Yeah. So for this problem, FP or full physics is the drag coefficient that we get through the simulation of this airfoil with these riblets.
The drag coefficient distributed next x, t, x, y, z time.
So this drag coefficient is the average drag coefficient.
That's so one parameter. That's why I'm saying you're fooling us, because that's one parameter. This is only one value. This is too much. Too many pictures for one.
No. Actually, if I want to be answering this quick. What we tried to do initially was to find the pressure distribution over the airfoil and predict the same thing. But the results that I have here is just for the drag coefficient. And the same thing is for the low fidelity one. The low fidelity is also the drag coefficient over the.
But that's, look, Amir, this is called co-kriging. If you can do that with co-kriging.
Yes.
It's a simple exercise co-kriging if you have one variable. Even if you have the field, like you mentioned, there's the pressure surface. That's a simple exercise of co-kriging.
So
what's the big deal?
I don't know the question right now.
The question is, what's new? Because what you just described to me, it's called co-kriging. Kriging is basically the base GP that geophysicists developed.
Definitely,
and then co-kriging also is developed. It's in Wikipedia. So I'm trying to I know these DARPA presentations because I'm a DARPA grantee and I know this group and other groups. And I want to see what is behind these figures because this problem in particular, because this is a really, really interesting problem, but there are many, many flaws which I couldn't start enumerating for this. Okay, for example, RANS uses wall functions, ad hoc wall functions, but actually for this problem, it's really the wall that you're trying to resolve. Never mind that. So RANS cannot be a high fidelity.
Just to be honest, I didn't do the CFD part. I cannot comment about the.
But the neural network part is trivial. I'm just telling you, it's really trivial if you have one coefficient CD, which is maybe a function of time or not, maybe not a function of time. It's the average one value, and you're trying to improvise for the one value, and you show errors. That's
actually actually trivial. I think it's something relative. You can have a neural network, and what's the level of the accuracy you can get. The question is not about how much simpler or complex the model is. The question is about what is the level of the accuracy you can get. So for example, if you're using the neural network and you get 1%, it's trivial. If you get 0.01%, it's not trivial necessarily. So that's my understanding. Based on the different problem, the goal is not always to decrease it to 5%. Sometimes the 5% is a very good error for us. Sometimes 5% is not even acceptable because, for example, for this special problem, the change of the drag coefficient itself is very small. So
Amir, I know this problem. Amir, I know this problem. You have to go and see how many papers I wrote on this, okay, including general fluid mechanics papers, not AI papers. So that I don't need to get a lecture on this. And I know that the accuracy, and I know that the optimum spacing, the S that you have there has to be 770 in wall units. And I developed that, okay? I was the first to do DNS with NASA Langley. That's my need. I don't need that. I'm asking the question. Here, you show a very complex problem, but then you optimize one value, CD, using GP. And I'm telling you, there is, we call it now multi-fidelity GP, but actually that's nothing else but co-kriging that was developed a long time ago. It's in Wikipedia. So I'm asking, what's the contribution?
I must
on the algorithmic side. On the algorithmic side.
Yes, I must look exactly what this co-kriging is. But algorithmic side thing here, we had about how to use it with our architecture and how train our architecture using GP when it's using GP. But definitely there are other answers here, and necessarily it's not the most optimal thing to do. If I want to say what is the algorithmic advantage in this example, there's not so much algorithmic advantage on this example. This is just to prove that it can work for extrapolation and it can work with different data-driven model, not only neural network, but also a Gaussian process. But beside that, this is mostly a paper about application.
Well, if you want to show that, if you want to show extrapolation, why don't you go back to your function? And you should. I have a function that I can ask you to extrapolate, similar to your function. I can send it to you.
One?
Yeah.
Okay.
Yeah. So I can send a similar function. I can send to you where you don't have data, I want you to extrapolate there.
We don't have any data?
No data.
No data at all.
No.
If we don't have any data at all from the high fidelity, we cannot get something more than the partial physics for ourselves. But definitely, if we have limited data, yeah, the accuracy is going to change. So yeah, I will be glad to test it. I mean, if you send it, I will test it with our frameworks.
I will, actually.
That's a great thing. Yeah, I really appreciate it.
Okay. And Rui?
Yeah. Okay, is there any other questions for Amir? If not, that's thank Amir again for giving this presentation, and hope that everyone, yeah, thank you very much, and hope that everyone have a good weekend and see you next week. Yeah, bye-bye.